Table 250.122 outlines the requirements for sizing equipment grounding conductors. The table heading refers to the rating or setting of the automatic overcurrent device in the circuit ahead of the equipment, conduit, and so on. This means you need to consider the overcurrent protection device that's upstream or on the supply side of the equipment you're grounding. Let's examine the two scenarios to clarify how to apply Table 250.122 correctly. In the first situation, there's a 1200 amp main circuit breaker, or MCB, feeding a wire array. This wire array then supplies multiple 200 amp meters and disconnect. The conduit used is polyvinyl chloride, or PVC. The question is whether the equipment grounding conductor for the 200 amp disconnects needs to be sized based on the 1200 amp main circuit breaker. According to the National Electrical Code, or NEC, the code official is correct. Table 250.122 dictates that the size of the equipment grounding conductor is determined by the rating or setting of the overcurrent device ahead of the equipment. In this case, the 1200 amp main circuit breaker is ahead of the 200 amp disconnects. Therefore, the equipment grounding conductor for each 200 amp disconnect must be sized as if it were protecting a 1200 amp circuit. Referring to Table 250.122, a 1200 amp overcurrent device requires a 3/0 copper equipment grounding conductor. This is because the table specifies a 3/0 copper conductor for overcurrent devices rated 1200 amps. Now let's look at the second situation. A 400 amp main circuit breaker panel board feeds a 100 amp branch breaker and feeder. The code official believes that the 100 amp feeder must have a number 3 ground, unless the conduit is all metal and serves as the equipment grounding conductor. A number 8 ground was installed for the 100 amp feeder. In this scenario, the code official is incorrect. Table 250.122 applies specifically to conduits or other enclosures that house the overcurrent device. Because the conduit in question does not contain the 400 amp main circuit breaker, the equipment grounding conductor size is not determined by the 400 amp breaker's rating. Instead, the equipment grounding conductor size is determined by the rating of the overcurrent device applying the feeder, which is the 100 amp branch breaker. According to Table 250.122, a 100 amp overcurrent device requires a number 8 copper equipment grounding conductor. Therefore, the initial installation with the number 8 ground was correct. To summarize, firstly, when sizing equipment grounding conductors, always refer to Table 250.122 in the National Electrical Code. Secondly, identify the overcurrent device that is directly ahead of the equipment you are grounding. Thirdly, if the conduit or enclosure contains the overcurrent device, use the rating of that device to determine the minimum size of the equipment grounding conductor from Table 250.122. Fourthly, if the conduit or enclosure does not contain the overcurrent device, size the equipment grounding conductor based on the overcurrent device that directly feeds the load or equipment in question. Applying these principles ensures that the equipment grounding conductors are properly sized, providing a low impedance path for fault current and minimizing the risk of electrical shock. Understanding the correct application of Table 250.122 is crucial for electrical safety and code compliance. Always consult the latest edition of the National Electrical Code and seek clarification from qualified professionals when needed. Correctly sized equipment grounding conductors play a vital role in protecting people and equipment from electrical hazards. When a fault occurs, such as a short circuit, the equipment grounding conductor provides a path for fault current to flow back to the source, tripping the overcurrent device, like a breaker or fuse, and disconnecting the circuit. If the equipment grounding conductor is too small, it may not be able to handle the fault current, potentially leading to a rise in voltage on the equipment enclosure, which could create a shock hazard. Furthermore, an undersized equipment grounding conductor may not provide a low enough impedance path for the fault current, which could prevent the overcurrent device from tripping quickly enough, increasing the risk of fire or equipment damage. In the first scenario, where the 1200 amp main circuit breaker is ahead of the 200 amp disconnects. Sizing the equipment grounding conductor for the 1200 amp breaker ensures that the fault current from any of the 200 amp circuits can be safely carried back to the source, allowing the 1200 amp breaker to trip and clear the fault. This is particularly important in situations where there are multiple loads or disconnects fed from a common source, as the potential fault current could be significantly higher than the rating of any individual load. In the second scenario, where the 100 amp branch breaker feeds the load from a 400 amp panel board, sizing the equipment grounding conductor based on the 100 amp breaker is appropriate because that is the overcurrent device protecting the circuit. The 400 amp main circuit breaker protects the panel board itself and the feeders to the branch circuits, but it does not directly protect the individual loads connected to the 100 amp branch circuit. Therefore, the equipment grounding conductor for the 100 amp circuit only needs to be sized to handle the potential fault current that could occur in that specific circuit. It is also worth noting that the type of wiring method used can affect the requirements for equipment grounding conductors. For example, if metal conduit is used as the equipment grounding conductor, it must be properly sized and installed to ensure a continuous and effective ground path. In some cases, a supplemental equipment grounding conductor may be required in addition to the metal conduit. Additionally, there are specific rules for grounding separately derived systems such as generators or transformers, which must be followed to ensure proper grounding and bonding. In conclusion, understanding and applying Table 250.122 correctly is essential for electrical safety and code compliance. Always consider the rating of the overcurrent device ahead of the equipment, the type of wiring method used, and any other relevant factors when sizing equipment grounding conductors. When in doubt, consult with a qualified electrical professional to ensure that the installation meets all applicable code requirements. Equipment grounding is a critical aspect of electrical systems, and proper grounding practices are essential for protecting people and property from electrical hazards. The equipment grounding conductor, or EG, is a vital safety component in electrical wiring systems. Its primary function is to provide a low impedance path for fault current to return to the source, enabling the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and interrupt the flow of electricity in the event of a ground fault. A ground fault occurs when an ungrounded conductor, like a hot wire, comes into contact with a grounded metal part of an electrical system, such as the enclosure of an appliance or a metal conduit. Without an effective equipment grounding conductor, this fault current could flow through unintended paths, like the human body, resulting in electric shock or electrocution. The equipment grounding conductor also plays a crucial role in minimizing the risk of fire. When a ground fault occurs, the high fault current can generate significant heat, which could ignite nearby combustible materials if the fault is not quickly cleared. By providing a low impedance path for fault current, the equipment grounding conductor helps to ensure that the overcurrent protection device trips rapidly, limiting the amount of heat generated and reducing the risk of fire. There are several types of equipment grounding conductors commonly used in electrical wiring systems. Firstly, a wire-type equipment grounding conductor is an insulated or bare copper or aluminum wire that is run along with the circuit conductors. This is the most common type of equipment grounding conductor and is typically used in non-metallic conduit or cable systems. Secondly, a metallic conduit or raceway can also serve as an equipment grounding conductor, provided that it is properly installed and meets the requirements of the National Electrical Code. This is often the case in rigid metal conduit, intermediate metal conduit, and electrical metallic tubing systems. Thirdly, a metal armor of a cable, such as armored cable or metal-clad cable, can also be used as an equipment grounding conductor, again, provided that it is properly installed and meets the code requirements. It is important to note that the equipment grounding conductor must be properly connected to the equipment enclosure and to the grounding electrode system to ensure a continuous and effective ground path. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, that is connected to the earth and provides a reference point for the electrical system. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit, as specified in Table 250.122 of the National Electrical Code. It is essential to use the correct size equipment grounding conductor to ensure that it can safely carry the fault current and provide a low impedance path back to the source. In addition to the equipment grounding conductor, another important component of electrical grounding is bonding. Bonding is the process of connecting together all metal parts of an electrical system that are likely to become energized, such as metal conduits, enclosures, and equipment frames. The purpose of bonding is to create a low impedance path for fault current to flow back to the source, minimizing the voltage potential between different metal parts and reducing the risk of electric shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal parts together. The size of the bonding jumpers is also determined by the size of the overcurrent protection device protecting the circuit. Proper grounding and bonding are essential for electrical safety and code compliance. It is important to follow all applicable codes and standards when designing and installing electrical systems to ensure that they are properly grounded and bonded. When in doubt, consult with a qualified electrical professional to ensure that the installation meets all requirements.